So thanks, and we are coming to the next talk given by Fabian Burghart on sharp threshold for factors in random graphs. So please start.
Yes, thank you for the nice introduction. Indeed, so this is joint work with a number of people. So Annika Heckel is from Uppsala, Mark Kaufmann is in Zurich, Noela Müller is together with me in Eindhoven, Matthias Pasch is in Munich. And what is this about? So we're studying factors. So we fix a small graph f on some number r vertices. We have a large graph G, which is n vertices. And maybe this picture shows the idea best. So if this thing over here, K4 with a missing edge, is my f, then this picture shows an f vector, meaning I can partition the vertex set into copies of f. And if you want to be very precise, then this picture actually shows 6 different f vectors, because for the blob here in the top right, you have 6 different choices of which edge you want to kick out. Yeah. Okay, and the natural special case that you might think of is if my f is just a K2, so like 2 vertices with an edge between, then an f vector is just going to be a perfect matching. So this is, has been studied for a long time. And I should say the one caveat is, of course, for this to work, we require that R divides N, which we'll always assume. I'm not going to mention this again. So that's not going to be an obstacle. But then the central question is, okay, if I have a graph, when does it contain such an f vector? And let me mention here another natural obstacle. So if I have a vertex that's not contained in any copy of f, then I cannot have an f vector, because then this vertex cannot belong to any sets of the partition. Okay, so then the second term in the title was sharp threshold. So what's a sharp threshold? We're looking at G and P, the usual Erdős-Rényi random graph. P is allowed to depend on N. And then we say P star is a sharp threshold for some graph property if whenever I'm 1 minus epsilon below the sharp threshold, the probability that this property holds will go to 0. And conversely, if I'm 1 plus epsilon above this threshold, the property holds with high probability, so with probability going to 1. Okay. And well, now you might have guessed that what we want to do is we want to determine the sharp threshold for the existence of f vectors in G and P. Not for arbitrary f, that would be a bit of a tall order. So we restrict ourselves to strictly one balanced graphs, where you have this notion of a one density of a graph. So you take your f, you look at the number of edges in f, and you divide it by the number of vertices minus 1. The minus 1 makes a lot of these things more elegant. So it turns out if you look at covers and factors, this is the right notion of a density, but it's maybe a bit artificial like this. And then, well, we say a graph is strictly one balanced if whenever I take a subgraph of the strict subgraph of this graph, the density of this subgraph is going to be strictly less than the density of the entire graph. So no strict subgraph has the same or larger density than the entire thing. And it's a rather diverse family. So all complete graphs are in there, all cycles are in there. Not quite all complete bipartite graphs are in there, but if you have at least 2 vertices on either side, then it will be strictly one balanced. Okay, and so indeed, here's our main theorem. This expression, or equivalently this one here, is going to be the sharp threshold for the existence of f vectors if f is strictly one balanced. So I should say this improves a breakthrough paper from 2008 by Johansen Kanbu. They determined the weak threshold, meaning they figured out that, well, this term to the power of 1 over s is sort of the right asymptotic, but they didn't have the constant factor in front. And also, if you restrict to a slightly smaller class of graphs F, then this result has been obtained by Riordan. And I will say more on this as the talk goes on. Okay. So how are we going to prove this? Well, we need matching upper and lower bounds. And the lower bounds are going to come from the obstacle I mentioned earlier. We need every vertex to be contained in a copy of F. So this is what's called an F covering. And then the upper bounds, well, we're going to talk about hypergraphs for this, but we'll get there. Okay, so as I said, the lower bound comes from, we need an F covering to have an F factor, so this is always going to be true. And it will turn out that we have equality, and this is not unprecedented. So Elders and Rini looked at perfect matchings, and they found these two thresholds coincide. The ln over n. If you actually compare this with our result, it's perfectly consistent. Wuczak and Troczynski later showed that if F is a tree, then you also have equality. And it's maybe more interesting because trees are not strictly one-balanced. And it turns out that indeed this cover threshold has been completely solved. So the full theorem is actually contains more than this, but we only need this case, and well, it matches with our threshold, of course, which is the idea, and this gives us the lower bound. And I should say, it's not always the case that this lower bound is strict. So indeed, for some graphs, like here, where the minimal degree is strictly smaller than the maximum 1 density. So here you have minimum degree 2 from these vertices over here, but then this clique here in the middle gives you 1 density 3. So here indeed the two thresholds will differ. However, Troczynski in that same paper conjectured that the thresholds coincide between coverings and factors if F is strictly one-balanced, and indeed we showed that this is the case. Okay, so let's talk about the upper bound, and this is the difficult part. So once again, going back to the result by Elders and Rini, you want to have the threshold for a perfect matching or a K2 factor, and it's this, and it's the same threshold where isolated vertices disappear. And it's also the sharp threshold for a bunch of other things in GMP. So you might generalize this to a different direction rather than looking at different F factors here. You might ask, well, if I instead look at a random R uniform hypergraph, meaning your potential edges are just all collections of R vertices, and you include them independently with some probability pi, when does this R uniform hypergraph contain a perfect matching? So you can imagine perfect matching here. This is the edges that are in red, and the hypergraph is just the entire thing with the red and blue edges. And this was resolved 6 years ago by Jeff Kahn. And he showed that, well, this sharp threshold is here at ln n over this binomial coefficient. And once again, it turns out that this coincides with the sharp threshold for the disappearance of isolated vertices. Okay, now how does this help us? We're interested in F factors, in graphs, not matchings and hypergraphs. So here's the vague idea and false idea for the upper bound. So we take our random hypergraph with pi prime large enough to ensure that we have a perfect matching. And now we are just going to replace every hyper edge with a copy of F on the same vertex set. And then, well, we say that this would give us certainly a graph where we have an F factor, right? And yeah, so there are some problems here why this idea, as it's stated, cannot work. So first of all, unless I'm looking specifically at complete graphs, I have more than one copy of a graph on a given vertex set. How do I know which one to use? The second problem is this won't actually give the lower bound because we had this constant factor in front, and you don't get this out of Treff-Kahn's result. The third problem is that, well, hyperedges in the hypergraph are going to be independent, but copies of F in G and P won't be independent because they can overlap. And then finally, the resulting graph may not even be distributed like a G and P. However, you can kind of work around this. So first of all, what we're doing is we're looking at HF and pi. So this is a random F graph. Think of this in the following way. So on every set of our vertices, you have you're going to have R factorial divided by odd F, many potential copies of F. And for each of these copies, you assign a hyperedge. This is potentially a multi-hypergraph. And then you include each of these edges, each of these hyperedges, with independently with probability pi. Yeah? So now if I look at HF and I look at one F edge in there, I know exactly which copy of F this should correspond to in GNP. And actually, this will also fix the second problem because it turns out to make this work, this pi needs to be slightly different from this pi prime. I'll say a few words on this later. Okay, so roughly this fixes problems 1 and 2. And for 3 and 4, we're using a coupling that was first developed by Riordan, then extended by Annika Hecke. And this will fix the other 2 problems, and I will say more on this now. So what do we want to do? We want to couple the Alder-Schwenni random graph with this random F graph in such a way that, well, P and pi, the probabilities correspond to one another, which means that, well, to see a copy of F, you need S, so P to the S, where S is the number of edges as a probability, right? So this P to the S should correspond roughly to this pi. And what you now do is you go through all potential copies of F, all of them, one by one. And you essentially, sometimes you'll decide to include this in G, and then you keep track of it in H. So you compute this conditional probability about whether you should see this copy in G. If this is large compared to the pi, then you toss a certain coin, and well, if this is a success, then and only then do you test whether you actually see this copy in G. And if you decide to test it, then you record the decision in H. So that's the one case. The other case is maybe this conditional probability is small. Then you only test in H whether you should see the hyperedge. And if then you get a yes, then the coupling sadly has failed. And then, so you go through this. Sometimes you decide whether or not you see a copy Fj or not. Hopefully you survive. And in the end, you're going to have a hypergraph and a G that has, they both have the correct distributions. And now, indeed, every hyperedge in H will also have the corresponding copy of F in G. Okay, and we now need to make sure that this works. So what we need to show is the probability that this coupling fails goes to 0. And it turns out there is a graph theoretic obstruction to this, which maybe counterintuitively comes from having too many copies of F in G that do not correspond to hyperedges in H. I say counterintuitively because in principle, if you want to see an F vector, then having more copies of F is always good. But it turns out if you have too many of these copies, then it ruins the conditional distributions. So what can happen is you can have in this picture here the three green copies of K4 with a missing edge. And if they are arranged like this, then you actually see, for example, this red copy that doesn't come from one of the green hyperedges, right? So when Riordan developed this coupling, he proved this following lemma. So if F is one balanced, then every such induced copy of F, like above here, either comes from an avoidable configuration or from a clean F cycle. Okay, so avoidable configurations basically just means I have a small subgraph bounded in size with too many cycles in it. And then I can exclude it simply by, well, a first moment argument. The other case is these clean cycles. So there's a cycle of, well, F edges such that the previous and the next hyperedge overlap in exactly one vertex. There's the special case over here. Oops, that's not what I want to do. There's a special case over here where you can have a cycle using only two edges, in which case it will look like this. And this case will indeed cause problems later. Okay, so the problem is these induced copies kind of ruin the coupling. So indeed, what Riordan did, and this is what I said earlier with the nice graphs, he restricted his attention to a class of graphs where he could assure that, if I go back, where he could assure that this second part just doesn't happen. So F is nice essentially just means that every induced copy is induced by an avoidable configuration. So you didn't have to worry about clean cycles. So the problem then was that K3 triangles are not nice. And to deal with that case, Annika Heckel developed modification or extension of the Riordan coupling. Well, the idea is, well, you first couple the clean cycles. So you couple these configurations with the corresponding, let's call them shadows in GNP. And then conditionally on that, you run the Riordan coupling on whatever remains. Okay. This works if the expected number of clean F cycles that you have in HF coincide with the expected number of the corresponding shadow graphs, which you get if you replace all of these hyperedges by the corresponding copies of F. And of course, well, these expected numbers need to coincide using, once again, the fact that pi is asymptotically equivalent to P to the S. Okay. So what does this condition mean? Well, if you write down and explicitly compute this, this expectation, then what you get is these expectations coincide if your F cycle is of length k and the corresponding shadow graph contains k times S edges. So basically every hyperedge contributes exactly S edges to the shadow. And maybe if I go back, you can see that this will be the case, for example, here, because each of these blobs contributes S edges and they cannot possibly overlap in an edge. But you can see that over here, in these clean cycles of length 2, that's not necessarily the case. It could be that both copies of F have an edge in this intersection. Yeah. So this is this scenario. And once again, you have one copy of F over here and one copy of F over there. And well, you can see you have a missing edge in here, which means that such a configuration will not appear with probability p to the ks, but it will appear with probability p to the 2s minus 1. So a factor of 1 over p too often. Okay, so what's the idea? Well, the idea is we simply introduce an extra dummy edge. So dummy edges are just, well, you have one dummy edge for every potential sparse clean F cycle in your graph. And now you do the following. You look at this G star NP. So it's going to be the usual Alder-Shreni random graph. But now you have the additional dummy edges that correspond to these sparse clean F cycles from the previous slide. And you include those also with probability P independently of everything else. And you simply declare that a sparse clean F cycle in G star is going to be, I see all of the usual edges, but also the corresponding dummy edge. And this fixes the problem of the missing edge. However, so this fixes the problem of the missing edge, meaning you can now run the Riordan-Heckel coupling between HF and this G star. Yeah. So meaning you can couple the sparse clean F cycles to the sparse clean F cycles in here, where we fix the problem of the missing edge. You can couple the regular clean cycles that are not sparse with here, because you don't need any dummy edges, so the probabilities work out. And then conditioned on this, you run the Riordan coupling on whatever remains, and you get HF and G star with the right probabilities, and you can forget about dummy edges afterwards. And then if you forget about the dummy edges, then on this side, you will just have G and P. Okay, so what this means is, well, if you then show that you can actually do all these things, you get the following result. So for all P up to our threshold plus a little bit, there exists a probability pi that is related in the correct manner. And the coupling between G and H, namely this one here, such that with high probability, every F edge in H also has the corresponding copy in G. Yeah? And now I can use another coupling between this HF and the R uniform hypergraph, where we know the threshold for a hypergraph matching, where pi prime and pi are related to like this. And now if I plug in Kahn's threshold for the hypergraph matching here and go through all of this, then it will produce me the desired upper bound that we need to make the proof work. Okay, so then let me finish by saying a little bit about some possible extensions. So you can be more precise than sharp hitting, sharp thresholds by using hitting time results. So now imagine, rather than fixing a probability P, you throw in edges one at a time. And then you have this classical result due to Bolovash and Thomason, where they showed that not just the sharp thresholds for perfect matchings coincide, but indeed, if you go through this random graph process, with high probability, the first time you see a perfect matching is also going to be the first time you stop seeing isolated vertices. And this extends. So my co-authors showed in 2024 that if you have KR factors, so click factors, still the same is true. So the first time you see a KR factor is going to be the first time you stop seeing a vertex that's not contained in any copy of KR. Oops. This then could be extended. So for this class of nice graphs that Riordan considered, we managed to show that the hitting times there agree as well. And we're currently working on the hitting time result for one balance factors, though once again, it turns out that the sparse clean F cycles are an obstacle there. And then on a related note, Morris and Riordan put up a paper on arXiv last month, where they talk about actually quantifying the results about the difference in distribution between copies of, in their case, a complete graph in GNP and hyper edges in the hypergraph. Okay, well, thank you.